This lesson is about trigonometry, and we'll start with probably the first thing you learned about when you learned trigonometry in high school. You would have defined the trigonometric functions in terms of ratios of side lengths of a right angle triangle. So here we have this right angle triangle. The bottom left angle is labeled theta. In the right hand corner there's a square. That square indicates that that angle is 90 degrees. The sum of the angles in the triangle add up to 180 degrees, and that means we have the theta side plus the 90 side plus this side is equal to 180. So this side must be 180 minus theta minus 90. So 90 minus theta must be equal to that angle. Usually we don't need to know that, but sometimes you do. I won't bother writing it down. Now the side opposite the angle theta, so it depends on where we put theta. The label that we're going to use for the sides will change depending on where theta is. So if I move theta up here, then the labeling will change accordingly. But wherever theta is, the side of the triangle that's opposite to that angle, we'll label as the opposite. The side that is opposite the 90-degree angle, we will always label the hypotenuse. And then the other side, the side that is not the opposite and not the hypotenuse, we'll label the adjacent. It's next to the angle, but not the hypotenuse of the triangle. We can define our trig function, sine, cosine, tan, in terms of opposites and adjacent, and memorize those relationships using the SOH. So, S-O-H, sine is opposite over hypotenuse, C-A-H, cosine is the adjacent over the hypotenuse, and tan, T-O-A, tan is the opposite over the adjacent. Thinking about geometry in a very basic way, if we were to take that hypotenuse and fold it down, so imagine this angle theta being something that we could squish down by taking this whole side and just pushing it down towards the adjacent. We can see that the adjacent cannot possibly be larger than the hypotenuse. And the opposite cannot possibly be larger than the hypotenuse either. The hypotenuse has to be the biggest of these three sides. So I put that down here, that the hypotenuse is larger than or equal to the adjacent, and the hypotenuse is larger than or equal to the opposite. Looking at the ratios, sine is opposite over adjacent, so something that's smaller than the hypotenuse divided by the hypotenuse, that tells us that the sine of theta cannot be larger than 1. There are extended angles outside of this first quadrant. Some of those angles are negative, and it's going to be important to also know that the sine of theta cannot be more negative than -1. Cosine has the same property. The cosine of theta is always between -1 and +1, and it all has to do with the hypotenuse being bigger than the opposite and bigger than the adjacent. Tan theta has no such restriction. The tan of theta can take on any value from -infinity to +infinity. One thing we'll do with these functions is we'll evaluate them at different angles. We'll use only selected angles, the nice angles like pi over 2, pi over 3, and pi over 4. Implicit in the statement I just made is that we will be working in radians, not in degrees. Radians are the natural units for trigonometric functions in calculus. Degrees are very artificial and not respected well by calculus. So I mentioned that we're going to look at extended angles. That triangle that I drew out, all triangles, all right angle triangles can be imagined as existing inside this first quadrant. This first quadrant contains angles from 0 to 30 to 60 to 90 degrees and everything in between. But we could also take that triangle and rotate it and invert it or flip it and imagine it exists in some other quadrant and label the angles differently. What we do is we imagine a circle and imagine slicing that circle up into pizza slices. We can have pizza slices of different sizes. The larger the slice, the larger the angle at the point part of the slice. The measurement of degree has nothing to do with any pure math reason for 360 degrees to be the division of a circle. It has to do with Earth. It has to do with the Sun-Earth relationship. But it has been imported into mathematics, and once in a while we'll talk about it, like I'm talking about it right now. So the 360 degrees just means we take the unit circle and we make 360 pizza slices. Each one's the same size. The corresponding degree measure at the sharp part of each of those slices or each of those sectors is 1 degree. It's 1 degree wide. So we say 360 degrees makes an entire circle. 180 degrees, which is 1/2 of 360, makes half of a circle. The more natural unit to measure circles in is called radians. Pi radians gives you half of a circle. 2 pi radians thus gives you the entire circle. I'll explain how to convert from one form to the other form. Another thing that we'll talk about with both respect to angle measurements is the partitioning of the unit circle into 4 quadrants. The first quadrant in the top right is the one that's most familiar to us. I'm going to call it the A quadrant, where A stands for all, and you'll see why I'm using this convention in a moment. To its left, but still in the positive y direction, is the S quadrant. So we start at angles of 0 over here. We increase our angle all the way to pi over 2, which is 90 degrees. And then as we increase past 90 degrees, that brings us into the S quadrant. So angles like 120, 150, they're here. Then we get to pi radians, 180 degrees. And if we go just a bit past that, we're into the T quadrant, which is angles between 180 and 270. And then down over here is 3 pi over 2, 270 degrees. And then if we increase the angle a little bit more beyond that, we're inside the so-called C quadrant. Now, it's getting a little bit ahead of myself, but I'm going to add this label in here. A stands for all. S stands for sine. T stands for tan, or tangent. And then C stands for cosine, or cos. And what this labeling refers to is whether or not each of these trigonometric functions is positive or negative in each of those quadrants. In the S quadrant, the output of a sine function evaluated at one of those angles in the S quadrant is going to be positive. The other trigonometric functions, tan and cosine, are negative in that quadrant if we plug in an angle in that quadrant. If we plug an angle in the T quadrant into all the trig functions, only the tan function outputs a positive number. The other two, sine and cosine, output negative numbers. And in the C quadrant, the cosine function spits out positive outputs, and the cosine and the sine and the tan spit out negative outputs if we plug in an angle inside that quadrant. The A quadrant, they're all positive. Sine, cosine, tan all give a positive output if we plug an angle in that's between 0 and 90 degrees. So I've been talking about radians and talking about degrees, and most likely you spent a lot more time in high school on degree measures and relatively less time on radian measures. So I want to show you how you convert from one to the other. One way is with a conversion formula. If you want to go from x degrees to radians, you would take the x and multiply it by pi over 180. So let's say you want to go from 120 degrees into radians. Well, you take the 120, multiply it by pi, and divide by 180. So first simplify by dividing out the 10. So 120 divided by 180 is 12 over 18. And then you can factor a 3 from the top and a 3 from the bottom, and then you can do, let's see what else. You can take another 3 from the top. So no, let's take 6, actually. I lied, a 3 and then a 2. So take a 6 from the top, a 6 from the bottom, and we'll get, and then cancel the 6's when you factor those out. you get 2 pi over 3 radians. And that would be our radian measure of 120 degrees. To go backwards, if you get a measurement in radians and you want to convert it into degrees because it's more familiar, you would take your radian measure, multiply by 180, and divide by pi. So it's the opposite operation, replacing multiplication by division. To go from 7 pi over 6, so you look at that, what does that mean? Well, 7 pi over 6, take the 7 pi over 6, multiply by 180, and then divide by pi. 180 divided evenly into 6, you get 30. The pi's cancel, so you have 7 multiplied by 30, which is 210 degrees. I'll do a few more conversions. So I'll go from 0 degrees to 0 radians. That one's easy. We have 0 multiplied by pi over 180, which is 0. Now to go from 30 degrees to some number of radians, we're going to have 30 times pi over 180. 30 over 180 is 3 over 18, canceling the 10s. And then we can factor 3 out of 18, cancel the 3s, and we get pi over 6. I mentioned that this is one way to do it. Another way is by memorization. There's some key angles, 30, 45, 90, 60, and you just memorize what those convert to into radians and vice versa. So if, for example, if you see pi over 6, knowing immediately that that means 30 degrees is the most efficient way to deal with the radian to degree conversion. Relying on a formula like this is slow. And then if it's 25 degrees, you just say, oh, it's just a little bit less than 30 degrees, so it's a little bit less than pi over 6. Usually that'll do what you need. Okay, 45 degrees, what do? 45 times pi over 180. This is a bit harder. I would begin by factoring out 5. So you have 9 over, what is that, 16? No, I'm a liar. 40, 30, I can't do that in my head. 36, I think. Anyway, maybe not, maybe that's not the fastest way. Instead, you could imagine, get rid of the 10, so you have, oh, you can't get rid of the 10s, 45, 180. Okay, you can say 180 is 90 times 2, and 90 is 45 times 2. So you have 45 times 4 in the denominator, and you can cancel the 45s top and bottom, so this is pi over 4. I'm trying to just do as much as possible without whipping out a calculator. So there's different tricks you can use without having to do any carry arithmetic. Okay, now how about the reverse? Going from radians to degrees. So pi over 3 measure. We're going to take our pi over 3, multiply it by 180, and divide it by pi. So the pi's are going to cancel. We have 180 divided by 3, which is 60. So that's 60 degrees. How about 90? So now we're going the other direction again. 90 divided by 180. So 180 is 90 times 2. We can cancel the 90s and get a pi over 2. And so on. We can do all the rest of them using these conversion formulas or by memory. 3 pi over 2 by memory. 2 pi, what does that correspond to? That's the whole circle, 360 degrees. Pi, that's half of a circle, 180 degrees. And then 5 pi over 6. A few different ways we can do this. We can do pi minus pi over 6. So 180 minus 30, 150, which is faster than using the conversion formula. And I think it's right. 155 pi over 6, yeah. So I'll write that down as a shortcut. Pi minus pi over 6, just a faster way to do the conversion. And I know these things are generally not taught, like these types of manipulations aren't taught anymore in high schools because of the reliance on calculators to do these types of calculations. But I think a lot is lost when you're not forced to think this way about mathematics. We're not forced to think about smart ways to do calculations. If the calculator just takes all that over for you. All right, well, we could take each of these angles, plug it into a trig function, get the corresponding y value, get the corresponding output, make that table of values, and then make a graph based on that table of values. It is a very tedious exercise to go through that for any of the trig functions, at least if you want to use enough points to get a good picture. So what I've done here is I've just made the picture for you. You can trust it and you can use it. You can also use software to graph it. That's fine. The sine function has this wave shape. Sine of 0 is 0, sine of pi over 2 is 1. And I'll go over some of those I'll go over explaining why those angles have those values and why, for example, sine of pi over 4 is 1 over root 2. I'll go over explaining some of that using SOHCAHTOA and using the reasonings around right angle triangles. But anyways, you get this wavy pattern, and this wavy pattern continues. If you go past 2 pi, you just get a copy of this piece over here. So do a copy paste of that box, copy it and paste it right over here. You just get like a shift of that graph as you continue to the right. And then you do it again, copy paste, copy paste, copy paste. It's like a pattern of that block that's there from 0 to 2 pi. And you can see that on the left-hand side. This piece here is a copy paste of the piece on the right-hand side. You could take it again and copy paste it over there and see what that part of the graph would look like. This is called a periodic function. It's a function that repeats over a certain period. The period in this case being 2 pi. A cosine function has a very similar looking graph. It's actually just a shift. You could imagine taking this peak here and pulling it 90 degrees or pi over 2 units to the left. Just pull it over. You get that. So there's a nice geometric relationship between the two graphs of the function, sine and cosine. That 90-degree shift, you might be able to make sense of that shift thinking about unit circles. Now here's an animation that describes a little bit about where those y values are coming from and why these functions become negative. So I'm going to pause the picture somewhere. I don't know if it's paused. Is it paused? Yeah, okay, I'll pause it right there. So we're currently inside the A quadrant at this phase of the picture. In the A quadrant, we're in the positive x direction and the positive y direction. So x is the direction going left and right, y is the direction going up and down. Okay, so we're in the positive x direction and the positive y direction. Now, I mentioned that the hypotenuse is always a positive quantity. We never allow the hypotenuse to become negative. The opposite and the adjacent, however, can become negative. The opposite is given by this green line. The length of that line is the opposite side. The purple line, which is kind of hidden right now, is the side that we call the adjacent. Cos is adjacent over hypotenuse. Sine is opposite over hypotenuse. If you look at this graph here, the y value of the cosine function is very small. That's because the cosine function involves the adjacent. And at this angle that we're currently at in the circle, where this yellow dot is up here, the adjacent is very small and the opposite is very big. We're about to reach the maximum size of the opposite, the largest the opposite can be. And look what happens as we reach that. Oh no. There, okay. So as we reach that point, the sine hit a peak, hit its max. And the cosine function went to 0 as we crossed that point. The adjacent went to 0. There was no adjacent when that angle was right at 90 degrees. That line was straight up. There was basically no triangle anymore. Once we cross that point, we're now in the negative x direction. And the adjacent has become negative. And look at the y value of the cosine function, adjacent of hypotenuse. We have something negative, the adjacent, divided by a positive hypotenuse. We end up with a negative y value. We can watch it as it continues its journey. So it's still negative, still negative. Look what's happening as we approach pi. As we approach pi, look what's happening to the opposite. I'll pause the graph. The opposite is getting very small now. It's going towards 0. And the y value of the sine function is going towards 0 as well because it's it's opposite over hypotenuse. the cosine function is becoming extremely negative. It's hitting a value of -1. You can see that the hypotenuse, where's my mouse? Let's see, well, it's not letting me. There. You can see that this hypotenuse and the adjacent are almost overlapping. So if you take something that's almost as long as something else and you divide them, you're going to get something close to 1. In this case, you have a negative quantity divided by a positive quantity, and the magnitudes are almost the same, so you're going to get something very close to -1. And that's exactly what happens as we hit 180 degrees, or pi radians. The cosine function's y value is going to become -1. We're also about to cross into the region on the circle, on the unit circle, where the opposite is going to become negative. So let's see that, when that happens. Okay, so now we're in the negative part. Okay, I'll pause it there. Now we're in the negative part of the quadrant of the in the y direction. So our y value is negative. Our x value is negative, going left and right in the purple. So both our sine and our cosine functions are negative there. But remember, tan is opposite over adjacent. I don't have the graph of tan showing, but the tan function will be positive down here. We'd have a negative number divided by another negative number, which cancels to make a positive number. Let's let it keep going. Okay, and then as that yellow dot crosses at 270 degrees, we're going to switch back to the positive x-axis and look at the y value. Look at the y value of the cosine function is flipped back to positive because it involves the adjacent, and the adjacent is in the x direction. We're now in the positive x, so it has become positive. And then we'll let the circle continue, the unit circle journey continue to its conclusion, back to the origin, back to the angle 0, or 2 pi. And it repeats over again. So that's where the graph comes from. That's why sometimes the y value becomes negative, sometimes it becomes positive. These graphs are always stuck between -1 and 1. You can't get outputs that are larger or more negative than that window. We'll continue in the next video.